Okay, we're going to be continuing our lesson from last week regarding DC circuits and specifically parallel circuits.
Yeah.
And perhaps looks like today's assignment is going to be what's actually called a complex circuit.
Yeah.
Which is a little bit of series circuits and a little bit of parallel circuit all mixed into one circuit. So let's review some of the concepts that we talked about before. Okay, so what does a series circuit mean to you at this point?
I want to say like it's but has more than one like input and output.
Okay.
Like there would be multiple batteries, but at the same time there would also be like multiple like light bulbs.
So based on what you're saying, I think you're referring to two different areas of the circuit. You can have batteries in series with each other, which means if you had a 1.5 volt AA battery in your remote and you stuck it like this with another 1.5 volt AA battery like that, then these are in series.
Yeah, I see. Yeah.
This is a battery pack. Battery pack is in series, and so the voltage in that case of this pack, of this series pack, would be the sum of voltage 1 plus voltage 2 plus however many you placed into it, which here would be 3 volts. So if you took a voltmeter and tested from end to end, it would say 3 volts.
Okay.
So when anything's in series, you're always to find the total amount of something in that series. You add up whatever that something is. If we're doing batteries, like we just talked about, the sum, the addition of all the voltages on all the batteries, you just add the battery's voltage on. You would add the voltage of battery 1 to the voltage of battery 2 to the voltage of battery 3, and so forth. On the other hand, you can have a circuit that has resistors. Remembering that this is the symbol for resistor, right?
Yeah.
So you can put these resistors also in series, end to end, like this. This would be a series circuit. If this was a 2 ohm resistor and this was a 2 ohm resistor, this was another 2 ohm resistor, then in a similar way where we're just referring to the total voltage of the series battery pack, in a similar way you say that the total resistance of all of these 3 resistors is R1 plus R2 plus R3 plus however many you have. So for us it would have been 2 plus 2 plus 2, 6 ohms, right?
Yeah.
And so if we dragged this battery pack over here and touched one end like that and one like that, and these are both 1.5 volts, now we can start talking about how much current is flowing because the battery pack is providing voltage. The circuit is closed, and so current will start flowing out of those batteries around the circuit. And how could we work out how much current is flowing? What law would we use to determine? Ohm's law. Yeah. And that's a very common, exercise in this type of problem. You would then use Ohm's law. You'd say that the voltage of the battery will be equal to the current in the circuit multiplied by the total resistance of the circuit, right? Matter to just solve for the current and plug in the values. If the total battery voltage was 3, as we had said, and the total resistance of the circuit was 6, then we'd expect a ½ amp flowing out of our batteries, right? How much of that current will go through this resistor here? We determined that a ½ amp, as we just did, determine a ½ amp is flowing out of our battery. How much of that will flow through the first resistor?
It'll be half an amp.
Yep, all of it. Because there's only one path, and all of it has to go through that path.
Yep.
How much would go through this one? The second resistor?
The second one?
Let's call that one R1, call this one R2, call this one R3. How much current would flow through the second resistor on the right?
If it reduces by 2 ohm. Would it be,
Remember, all the current has how many paths to go through right now?
3?
No, so when we talk about paths, if I draw like this all the way around, this is a hallway inside your school. You start here, and you keep walking. How many times do you have to make a decision in terms of which way you're going to go? In terms of, you got to get back to your starting point. I mean, you can get to this corner and consider this a decision, but it's not really a decision. Which way are you forced to go? Forced to the right. And then here, it's not really a decision. I mean, yeah, you could bang into the wall, but electrons don't do that. They seek out that path of least resistance. And they're automatically going to go this way, and they're automatically going to go this way. So how many paths do we have in that loop?
4.
That's actually 1. That's 1 path. Happens to curl around on itself to make 4 corners, that's true. But it's really considered 1 path. There's no spot where the electricity has to decide whether it's going to go left or right.
Okay. I see what you mean now. Okay.
If we had a corridor that now looked like this in a school, and then it went like that, we have 1 path here, but that 1 path is being broken up into 2 paths now, right? Some people will walk that way, some people will walk the other way. So do we have any forks like this in our path, in our series circuit?
No.
No, and that's the definition of a series circuit. Is there's only one forced route that all the electricity has to take, which means if this was, I don't know, let's keep going with this analogy. Some corridor in the school, and there's, let's say, 3 people, and they kind of stick together. They walk around as a group. They walk around like this. How many of them, if we have a gate here, how many of them will go through this gate? All of them. How many of them, if we put a gate here, how many of them will go through that gate?
All of them.
3. How many will go through this gate?
All of them.
All of them, right?
They say, so all 45 amps will go through all the resistors?
Correct, yep. A half amp would have to flow through the second resistor, because all of the electricity has to go through that resistor. And then lastly, how much would go through the last resistor, R3?
Half an amp.
Half amp, yep. And that's one of the laws and rules for series circuits, is that, I'm going to add it up here, that the current in amps flows equally through all parts of the circuit.
Gotcha.
Now you might think, well, the only reason it's, the same is because, in this simple case, he made 3 resistors and they were all 2 ohms, 2 ohms, 2 ohms, 2 ohms. And for that reason, and only that reason, some students might think that it's a half amp flowing through all 3 of them equally because they're all 2 ohm resistors. What would you say back? What would you say back to that? Is the reason that a half amp is flowing on the top, a half amp is flowing down on the right, and a half amp is flowing to the left on the bottom? So we're focused on the fact that there's a half amp flowing all around this. Is that only because each of these resistors are the same resistance, 2 ohms each?
No.
Exactly. What if the top one was 5 ohms and the bottom one was 20 ohms and the one on the right was 70 ohms?
Well, they would still be forced to go through each path.
Correct. Correct. Would it still be a half amp?
Yeah.
If the top one was some crazy weird number I picked out in my mind, 20 ohms, the bottom one was 70 ohms, one on the right is 54 ohms, will it still be a half an amp? Think about that.
No.
No, because what would have changed?
What do you mean? Like, yes, it wouldn't change.
Well, yeah, if I take all those resistors out and replace them with resistors that are random and completely different values, would the current in the circuit change, or would it still be a half an amp?
It would change.
It would change. Why would it change?
Because the resistance would resist some of the current.
Correct. The total resistance of the circuit, would it still be 2 plus 2 plus 2, which is 6 ohms?
No.
No, it would be whatever I said, 57 ohms. You have to add all those up. The total resistance goes up. What will happen to the current? Should it be more than half amp, or less than half amp if they were all big resistors like I listed?
It'd be less than half an amp.
Be less, because then again that ties us back to that idea that current, which I'm writing on the top left of the screen right now, is inversely proportional to the total resistance, right?
Yeah.
So if the total resistance goes up, the current would drop. But whatever it drops to, let's say it drops to not a half amp now, but now it's only 0.1 amps. Will it be 0.1 amps everywhere, even though there's completely different resistances in the different areas?
No.
Remember, this is a law, this one on top of the page here. So I'll add another note to that, which is regardless of different resistance areas. So let's say, for example, back into our hall analogy, that this gate here is a door, but it's jammed. So it takes them longer to get through it. They have to work to open it because it provides a lot of resistance, right?
Yeah.
But eventually, even though they deal with a lot of resistance getting through this top one, how many people, once they open it, will go through? Remember, where all of them, all three. Then they get to this gate over here, and the door is there, but it's opened. Very low resistance. How many people will go through? All of them. And then this one is also not completely open, not completely jammed, but something in the middle. But eventually, once they open it, how many people go through? All of them, right? So the current is the same everywhere, regardless of what the different resistances are in the different areas.
I got it.
Okay?
Yeah.
That's a law of circuit physics, physics law related to circuits. That if it's a series circuit, we're talking just about series circuits right now, right?
Yeah.
Right. How do we find out how much voltage drop? Which is to say how much voltage is being used on each of my 2 ohm resistors in my picture. How would I solve that?
By calculating each with Ohm's law.
So let me just erase this. Well, 1 second. I'm going to just clear out some of this. And I'm also going to show you that typically the batteries are not shown like pictures of batteries. They have a symbol for batteries, and I'll draw that symbol in so you're familiar with it, in the case that you're not already. So this is the symbol for battery. Have you seen that before?
Yeah, I have.
Okay. And we said it was a total of 3 volts because it was 1.5 plus 1.5, right?
Yeah.
So how do we find out how much voltage is being used on R1, the first resistor? Because that voltage is what pushes the electricity through the areas that have high resistance in the circuit. And if there's areas that are very high resistance, then it will use more of that 3 volts to push it through. But let me point out this very important idea. If you have a 3-volt battery like this, and then in order to get, because this is related to energy. Voltage is related to the energy in battery, right?
Yeah.
So, for example, it's like those people that were walking around the corridor. Let's say they have 100 units of energy, and they got to that first door, and it was jammed, like I had said, and they used, boy, quite a bit of their energy to get through that first door because it was jammed, and they used 60 units of their energy that they had, which they originally started with 100. That would be like a 100-volt battery. And they used 60 to get through that first jammed door. After they finally get through, how much is left?
How much is it? Like,
They started with 100 units of energy, and they used up 60 to get through the first jammed door.
oh, they'll be left with 40.
They'd be left with 40. And that's why we call that a voltage drop. The voltage drops, like the energy drops, because they don't have that energy available anymore. They've used it already to get through that door. And as they go on to the next door, there's whatever the amount of voltage remaining is whatever's left. Does that make sense? Okay, and so if this was our case here, I'm just going to draw this like this here again. And this was our 2-ohm resistor. And we did already determine that there was 1/2 an amp flowing right through that resistor because all of the people have to go through the door, as we talked about, which means all of the current has to flow through all of the areas. How will we find out how much voltage is being used on this one top resistor? Will the answer be 3 volts? Will they use 3 volts to get through that top resistor?
Yeah.
Don't they have some other doors to get through?
Yeah.
So they can't use it all on the first door. If they did, then what would happen to the kinetic energy and motion of the people? They use all of their energy to get through the first door.
We'll stop.
They would stop, which means, in my analogy, the circuit shuts down. But the circuit doesn't shut down. They keep on going after they get through that resistor. So with that idea, can you have all 3 volts used on that first?
No.
No. The other rule is that when the people make their way around this path, if there were 3 gates they have to get through, and they again started with, let's say, 100 units of energy, and there are 3 gates to get through, the rule is that by the time they complete the path and get all the way back around to their starting point, they actually have to be so exhausted that they'd lay down, meaning they've used all of their energy. That's another law of physics. So if they used 60 units of that energy that they had, which was originally 100, they started with 100, and they used 60 to get through the first gate, and then they used 20 to get through the next gate, then they have to use that last 20 to get through the last third gate, so that the total energy used was 60 plus 20 plus 20, which is 100, and that's how much energy they started with. They have to use all of their energy to get through all of the spots that have resistance. That's a law, and that law is actually called Kirchhoff's law. So how can we figure this out? I'm going to go ahead and tell you. We can use Ohm's law, V equals IR, right?
Yeah.
Because do we know the current I flowing through this particular resistor on the top? Yes. And do we know the resistance is 2 ohms? Yes. So we can determine the voltage, what's called the voltage drop on this particular resistor by just multiplying the current flowing through that resistor, which we already know is a 1/2 amp, because there's a 1/2 amp flowing through all parts of the resistor, and multiply it by what is the resistance of that resistor? 2 ohms. So 1/2 times 2, we would get 1 volt, right?
Yeah.
How much voltage drop would we have for them coming through the second resistor? They're on their way down now.
It would have.
We get to use the same idea that I just showed you. Voltage drop equals current flowing through that section multiplied by the resistance of that section. Remember, it was also a 2 ohm 2 ohm resistor. They were all, in my first problem that I have in the middle of the screen, all 3 of the resistors are 2 ohms.
Okay. Yeah, I see that. Yeah. Oh.
So this guy's also 2 ohms. How much current is flowing down this path on the right? How much is flowing through out of the battery?
0.5 volts.
Half amp. Remember, how much is flowing through the top resistor? Half amp. How much is going to flow through the resistor on the right? Half an amp. So now we have our two values to use Ohm's law. Voltage equals current times resistance. What would we get?
Voltage equals current.
We're using it just for that one resistor. So the voltage dropped on that resistor will be equal to the current that flows through that resistor multiplied by the resistance of that resistor.
You have one.
Exactly, you'd have one. Same. So from an energy standpoint, it's claiming that they would have used the same amount of energy, even though voltage and energy are not exactly the same. They're definitely related to each other. So in this analogy, they would have used 1 unit of energy to get through the top resistor, and also 1 unit of energy to get through the resistor on the right. Why would that be the same amount of energy to get through both?
Because they're the same.
Exactly. Same what?
Same resistance.
Same resistance. Exactly. If the door on the top was a little bit jammed, they'd use a certain amount of energy to get through that, and then when they get to the next gate, they find that the door is exactly jammed in exactly the same way as the first one. So they use the exact same energy to get through that one, right?
Yeah.
And for the very last resistor, how much voltage drop would be expected on the last resistor?
Yeah, one.
1. Yep. Again, because why?
Because it's the same resistance.
It's the same resistance. Yep. It's still yet another 2 ohm resistor. And so you'd say voltage is, again, current times resistance, a half amp times a resistance of 2 ohms, and we would get 1 volt. Now let's go back and check how much voltage was used. We used 1 volt here to get through the bottom resistor. We used 1 volt here to get through the resistor on the right, and then we used another 1 volt, which is right here, to get through the top resistor. So what is the total voltage used? 1 plus 1 plus 1. 3. How much voltage in the first place? It was a 3 volt battery, remember? Because it was 2 1.5 volt batteries stuck together.
Yeah.
So that's a law. The law is called Kirchhoff's law. Kirchhoff's law, which I'll spell for you. I won't write it all out, but I'm pretty sure in the last lesson I wrote it down for you, so you probably have it in your notes. But I'm just pointing out that idea again is called Kirchhoff's law. Kirchhoff's law is that all of the voltage drops have to add up to the voltage of the battery. So technically, the voltage drop, even though we called it 1 volt, it would actually be negative 1 volt, because when you lose energy, that's represented as a negative. When you gain energy, that's represented as a positive. So technically speaking, the voltage drop on the top is negative 1 volt, the voltage drop on the side is negative 1 volt, and the voltage drop on the bottom is negative 1 volt. So when you think of it that way, you say, okay, the total energy used is negative 3 volts, because negative meaning that energy was used up. And then when you compare that back to the battery's voltage, which was 3, they should be the same. And that's called Kirchhoff. And very, very lastly, what if it was one resistor that was 2 ohms and one resistor that was 4 ohms? So now they're not the exact same resistances, and it's still, let's say it's still a 3 volt battery. I changed it a little bit, because before we had 3 resistors, now we've got 2 resistors. And I've also changed it in the sense that they're not the same resistance, 2 ohms across the board. Now we've got 1 2 ohm, and now we've got 1 4 ohm. Who's harder to get through?
The second one.
Yep. So where will the most voltage be used?
In the second.
In the second one, right?
Yeah.
if it's twice as hard to get through this one, because remember, voltage equals current times resistance, and therefore, if is the current flowing through both of these going to be the same? The current flowing through the 4 ohm compared to the current flowing through the 2 ohm?
Yes.
Yes. Same current, because that's again the law on the top of the screen. So really, when we're looking at voltage drop compared to resistance, the voltage drop is proportional to the resistance of that resistor. So if you have a 4 ohm resistor compared to a 2 ohm resistor, everybody would agree that the 4 ohm resistor has more resistance. By what factor is the resistance greater for the 4 ohm resistor?
Factor of 2.
Factor of 2. And so since the voltage drop is proportional to the resistance, how much more voltage, by what factor will the voltage drop be greater for the 4 ohm compared to the 2 ohm? Voltage drop is proportional to resistance. So if the resistance is twice as much, it should use how much more voltage to get through the 4 ohm resistor?
Twice as much.
Twice as much, yep. And so what two numbers will add up to 3, and one of them has to be twice as big as the other?
Also 2.
2 volts would be used on the 4 ohm resistor. How much would be used on the 2 ohm resistor?
1.
1. What would they add up to? 3, because that's Kirchhoff's law. And it's also pointing out that more voltage would be used on the area that has high resistance because it's harder to get through. So there'll be more energy spent trying to get electricity through that area of high resistance.
Yep.
All right, does that make sense?
Yes.
All right, so let's move on. Quickly review parallel, and then we'll do the complex circuits. Let's say we have the same sort of problem. Not the same sort of problem, but the same values. So it's still going to be a 3-volt battery. And then this one was originally 2 ohms, let's say, and this one was 2 ohms. Now let's even make a third path, because we're comparing this, remember, to the very first thing I did with you, which was 3 different areas that all had 2 ohms, right?
Yeah.
So this was in series, 2 ohms, 2 ohms, 2 ohms, and a 3-volt battery. We did that already. Now we're just wiring it differently. Same thing, we got 3-volt battery. We still have 3 2 ohm resistors, but we're wiring them in parallel now, right?
Okay. Yep.
So the current will flow out of the battery as usual. But once it gets to this point here, some of the current will go down and the rest of it will continue straight. And then when this bit that's continuing straight gets here, some of that will split yet again, go down, and some of it will continue straight. Whatever continues straight will just continue all the way around, straight through this resistor. And then once it gets here, it'll recombine with the current that's flowing down here, and they'll rejoin into one flow of electricity. So these two come together, right?
Yeah.
And flow. And then this guy is coming down here. This joins the path as well, right? And so all 3 of them would combine back into one continuous path over here, back up. Does that make sense?
Yeah.
Okay. So let me erase that because it's messy, but it's showing an important idea. Okay, so one more time. 2 ohm. Oops, sorry. So now we have 2 ohm, 2 ohm, other 2 ohm. All right, do you remember how we're going to find the total resistance of this circuit? Now that we see it's not a series circuit, it's a parallel circuit.
Yeah.
Should it be more, the same, or less than the, remember back over here on the series circuit on the right, what was the total resistance?
On the series circuit, it was 3 volts.
Yeah. No, what was the total resistance on the series circuit?
The series circuit,
6 ohms. So now that we've decided to wire it in this other way called parallel, do you believe that the total resistance will still be 6 ohms, less than 6 ohms, or more than 6 ohms?
will still be 6 ohms.
That's a natural thing to guess, you'd think, because we're using 3 resistors and they all have 2 ohms of resistance, right?
Yeah.
But remember, the amount of paths is what can dramatically change how much resistance something that's flowing experiences.
Okay.
All of our body is all wired in parallel, all of the flow of blood, right? We do have arteries, but what do those arteries break up into? Veins, and then the veins yet break up again into capillaries. And it's your body's way of providing more paths for the blood to flow so that there's less resistance for the flow of your blood, right?
Yeah.
How about a 5-lane highway versus a 2-lane highway? Which one has the most resistance? 2-lane. Who has the least resistance? 5-lane. Again, for the same reason. 5-lane highway has more paths than a 2-lane highway. What if there were animals that wandered through the woods, and a lot of these animals walk in paths? If there's a certain area where they're all forced through one path, compared to this path breaks up into 3 different paths, which one would cause them to have more resistance? One path, right? So series, in this case, the series circuit should have more resistance. Because the series circuit only has how many paths? In this particular one, yeah, there's only one path. That's actually called a simple. In a simple series circuit is one path. How many paths have we made now on our parallel circuit? We can consider this as 1, but then there's a breakout right here, so that's 1 path. Then then there's a second path, then there's 3 paths, right?
That's 3 paths, yeah.
Yeah. So there's going to be less resistance here. So to find the total resistance of this circuit, we use this new math technique. And you would do this for however many you have, up to the nth resistor.
Okay.
And sometimes the notation for this, on the AP Physics exam equation sheet, it will show it as a sum symbol. It'll say, what will they say? I think they call RP. In fact, let me change it because it's not entirely correct. They show it as 1 over RP equals 1 over the sum of the resistors. So your sum is in the denominator on this series of terms. Okay?
Yeah.
So how will we put this to use now? Well, to find the total resistance of this circuit, yeah, we would do 1 over the total resistance, and that's what we're aiming for, because it's the total resistance that dictates the current. Right? The voltage also dictates the current. If it's a high voltage battery, it'll provide more current. If it's a low voltage battery, it'll provide less current. But given the fact that we're comparing these two, the series circuit on the top right and the parallel in the middle, which both have a 3-volt battery, then the fact that we have different resistances in each case is definitely going to affect how quickly they're able to flow. Where resistance is low, the flow rate is high. Things can move more easily. Where the resistance is high, the flow rate is low because the resistance is higher and it's harder to move along, right? So now when we're to actually calculate the total resistance, and again, we want to do that because we're going to eventually want to know how much current is flowing in our circuit. We would do 1 over 2 plus 1 over 2 plus 1 over 2. What would that get us? So you'd get 3 halves, right? So this is where you're at right now. You get 1 over the total resistance is equal to 3 over 2, because it's a half plus a half plus a half, which is 3 halves. And then to solve for the total resistance, we just flip or invert the left side and flip or invert the right side. Both of them just get flipped, right?
Yeah.
So when we flip it, we get the total resistance, because that's what we wanted to solve for, is the inverse of 3 halves, which is 2/3, right?
Yeah.
As a decimal, that would be 0.66 ohms.
Got it.
Now remember, each resistor had a resistance by itself of 2 ohms. Yet when wired in parallel, the total resistance is not even 2 ohms, not even 1 ohm, less than 1 ohm. It's trying to show you that the number of paths has a huge effect on the total resistance of the circuit, much more of an effect than the actual resistance of any particular area, of any particular resistor. The number of paths is a significant effect. That help? Okay. So now, how can we work out what the current coming out of the battery is? Maybe you can do that using Ohm's law. Because remember, the battery voltage is 3, and we now know the total resistance is 0.66 ohms. So now use your tools to figure out what is the current coming out of this battery. I'm sorry, 1 second. I was just trying to clean this up a little bit. Okay. So you used Ohm's law to solve for the current, which is the voltage of the battery. Well, yeah, what you're saying is right, but I'm actually solving for the current now. So current will be the voltage of the battery divided by the total resistance of the circuit. So we have 3 divided by, for the battery voltage was 3, divided by 0.66, which was actually 2/3, right? So as a fraction, it was 2/3. So 3 times the reciprocal, 3 halves, will give me 9 halves, which gives me 4.5, right? What will the unit be for current? What is it? Amps, good, yep. So there's 4.5 amps coming out of our battery. So now the question is, how can we figure out how much is going to go through each path? Because remember, it's like people, right? If this was 3 people walking in that hallway, like I said, as a group, and one of them decides to go down, then how many are going to go straight? If one of them decides to take the downward path, how many of them would continue on forward if there's a total of 3? 2, right? Yeah. That's an idea. That's an idea that at those splitting points, the current will split. So 4.5 will not all go down, 4.5 amps. And 4.5 amps will not all just continue forward. It's a splitting effect. Some will go down and some will go forward. All right? And so we're going to now try to work out how much of the current takes the down path, this first one, and how much of it stays forward. So there's another rule for parallel circuits. In series circuits, the current is the same everywhere. In a parallel circuit, like the one I'm showing you here, the voltage is the same everywhere. So that means that the voltage on the battery is 3 volts. That means that this first resistor will be 3 volts. The second resistor will be a 3-volt drop. And the third resistor will be a 3-volt drop. That's a huge change from the wiring of a series circuit. In a series circuit, the voltage of the battery gets distributed to all the different areas. In a parallel, all of the different branches, paths, get the same voltage as the battery. All right?
Yeah.
So that's an important, very important. I'll write that here. In parallel, all branches get equal voltage. So what I'm referring to as a branch is like this. When all of the wiring, that's in one wire, splits into two possible paths and then comes back together, that's referred to as a branch. And so if you ended up having a resistor on one side of the branch and a resistor on the other side of the branch, whatever the voltage is over here, I'm going to randomly say it's 7 volts. You know by this law that this other side is also a 7 volts on this other resistor. If one of the resistors was in this branch was not 7 but 2 volts on this side, then by this law it'll be 2 volts on the other side as well, because that's the law. The law of physics that on all branches there'll be equal voltages on both sides of the branch.
Okay.
All right?
Yeah.
So now that we know that, could we use Ohm's law again to calculate how much current is going through each of those resistors? Because we know the resistance of each, that's typically given in a textbook problem. And by this law that I've just described to you, we know that all of them are going to be 3 volts. So can we solve for the current flowing through each of them now?
Yeah. Okay.
Yeah. Can you try that? The nice thing about Ohm's law is it can be used in all different variety of cases.
Yeah.
You can use it for the circuit as a whole. You can use it for little different sections of the circuit. You can use it for series circuits. You can use it for parallel circuits. You can use it all the time.
So take the current of the first one and reduce it, right? It is going to multiple power.
Exactly. So what are you getting when you use Ohm's law to solve for the current going through, let's say, the first resistor on the left? The voltage on that resistor is 3 volts because it's a parallel circuit and it gets the same as the battery voltage. And the resistance of that resistor is 2 ohms.
Current is First is voltage divided by resistance.
Yep.
And 1.5 for the first one. And the current reduce that. Also, they're all the same.
Yep, exactly. So when you do voltage divided by resistance, you get 3 divided by 2, which is 1.5 amps, right?
Yeah.
So you get 1.5 amps that's flowing down this first path. How much will flow down the second path? Well, the second path is the same, 3 voltage, and it's also 2 ohms of resistance. So you get 1.5 amps flowing down the second path. And then again, the third path is also 3 volts and also 2 ohms. You get 1.5 amps flowing down the third path. What do those all add up to? 1.5 amps flowing down each of the paths all add to what value?
4.5.
4.5. How much was coming out of our battery?
3 volts.
No, that's the voltage. How much current was coming out of the battery?
4.5.
4.5. So does that make sense?
Yeah.
It's like having 3 people come out of the battery, and then one person takes the first path, the other person takes the next path, the other person takes the next path. They all add up to 3 because that's how many people came out of the battery.
Yeah, got it.
Right?
Yeah.
So it turns out that they're all equal current for what one reason? Well, for what 2 reasons, actually. Why is it that there's 1.5 amps flowing down each of those paths? There's 2 real reasons why it's all the same.
Same resistance.
Same resistance
voltage.
and the same voltage. You got it. What if now, on the other hand, one of the paths wasn't 2 ohms? Let me erase a little bit of this to make sure you understand that very important idea. Let's change it just a little bit. It'll still be 3 volts on all of them. I'm not going to change the battery voltage. Now, we're going to make this guy 4 ohms. And the other ones are going to stay 2 ohms here, 4 ohms in the middle, 2 ohms on the right side. Which path, let's call this path 1, path 2, path 3, which path will get the most current? And why? Remember, they're all still 3 volts, because that's a law for parallel circuits. They all get the same voltage regardless of how much resistance is on each path. So which path will get the most current? Path 1, path 2. In fact, let's change this one more time. Sorry. Let's change path 3 to 6 ohms. So path 1 is 2 ohms. Path 2 is 4 ohms. Path 3 is 6 ohms. In which path would you expect the most current?
The third path.
The which one?
When you say that, you mean current like as an output or input?
So just remember that the total current coming out of the battery is some amount. Before it, we said it was 4.5 amps. It wouldn't still be 4.5 amps if I changed it from 2 ohm plus, there was 3 2 ohm resistors before, and that made 4.5 amps. Now I'm saying there's a 2 ohm, a 4 ohm, a 6 ohm. That would change the current coming out of the battery. But the point is, whatever that amount of current is coming out of the battery, some of it's going to take the first path, some of it's going to take the second path, some of it's going to take the third path, and all of those have to add up to the total current coming out of the battery. In which of those paths would you see the most current? Path 1, path 2, or path 3?
Path 1.
Exactly, because that is the path of least resistance, and electricity will always send more electricity down the easiest, least resistance path, right?
Yeah.
So there'll be the most current taking this path. Then there's a in between, I don't know if you want to call that middle amount or median amount, whatever you want to call it. And then the least current would take path 3, because that has 6 ohms of resistance. And that's 3 times harder to get through than the 2 ohm path. But what will all of those currents in each of the paths all add up to? The current coming out of the... They'll all add up to the current coming out of the battery.
The battery, yeah.
Right? So let's now show how could we do this problem if we were asked to, because your homework problems are going to be similar to this. If it was, in fact, these new values, 2 ohms, 4 ohms, 6 ohms, why don't you try to solve for the total resistance of this circuit? Could you do that? Can you try this problem? Try to solve for the total resistance of this circuit.
Okay.
With a 2 ohm, a 4 ohm, and a 6 ohm in parallel.
What resistance you want me to solve for?
Yeah. That's always the first thing you should start with, is the total resistance of the circuit, because then you can solve for how much current is coming out of your battery. And that's always a good first step.
It's going to be 12 ohms of resistance. Did you hear me?
I'm sorry, I didn't hear you.
I said it's going to be 12 ohms of resistance.
Remember, that's only for series that you get to add them up like that.
We don't add them up for parallel?
No. Remember 1 over R1 plus 1 over R2.
Okay. So it's going to be...
So it'll take a little more time to work out the resistance of a parallel circuit for that reason, because you've got fractions to deal with. Where in a series circuit, it's much easier. You just add them together like you tried. I might need to call it a little bit early today, because I'm actually not feeling the sickness from my kids. I mean, I feel enough, well enough to have done it with you, but I don't know I'm going to be able to go the full 2 hours.
Okay, yeah,
Okay.
no problem.
Okay. Now let me remind you, do you have to do everything with fractions?
No.
No, you can just put it into your calculator. 1 over 2 plus 1 over 4 plus 1 over 6, enter, and just you can just get a decimal and then just approximate the decimal. That's totally fine.
Okay.
Math teachers are, of course, oh no, everything has to stay perfect, everything has to be fractions, let's find our lowest common denominator. Like, in the real world, when you're dealing with physics problems in a textbook like this, you don't need to be like that.
Exactly what I was doing.
Yeah, not to mention, like, your homework problems have one resistor is 750 ohms, the other is 680 ohms, the other resistor is 990 ohms. Yeah, good luck doing all that without turning it into decimals.
I got 0.9.
All right, I'm going to do it now. We have 1 over 2 plus 1 over 4 plus 1 over 6. So I know 1 over 2 is a half, 1 over 4 is 0.25, and 1 over 6 is 0.167. Yeah, 0.167. So I'm going to add those up on my calculator. 0.167 plus 0.75, and 0.917. But that's not our answer for the total resistance, right?
Yeah.
1 over the total resistance is 0.917. So how do we get the actual total resistance? Remember, we do the flip trick? Flip and flip. Because 0.917 is really over 1, right?
Yeah.
So you got to flip both sides now. So your total resistance will be 1 divided by 0.917.
You give me 1.09.
Yep. So the total resistance is 1.09 ohms.
Ohms, yes.
Yep. Now, how can we solve for the current coming out of the battery? This is step 2. All the sequence of the steps I'm taking you through are important because they're the steps you have to take. It's like having like a system of equations where you've got a bunch of unknowns. You have to start in one particular spot and solve for that one thing. And then once you have the answer, oh, now we can go get the second thing. And then once you got the second thing, oh, now we can go get the third thing. And that's kind of like what this is. It's a giant system of equations. And the first step is always finding the total resistance of the circuit, like we just did. Then the second step, find how much current is coming out of the battery, because you know now the voltage of the battery and you know the total resistance of the circuit. So you should be able to work out the current coming out of the battery, right?
Yes.
It's not actually 100% necessary to do that, but I'm just want you to do it because most physics prep questions in a textbook, that would probably be part B. Part A would often say find the total resistance of the circuit. Part B would often say find how much current is coming out of the battery. And then part C, they would ask determine how much current is flowing through each of those branches. So that's where we're headed. So are you working on getting current now coming out of the battery?
Yes, I am.
All right, good.
I mean, like, since you don't want to change the voltage of the battery since we already did this one, because it would still be 4.5 amps, right?
No. Remember, it was only 4.5 amps before when we had 2 plus 2 plus 2. We had 1/2 plus 1/2. And when we inverted it, we got 0.66 ohms.
Okay.
Now that we have a 2, we don't have a 2 ohm, a 2 ohm, a 2 ohm anymore. Now we got a 2 ohm, a 4 ohm, and a 6 ohm. And as you just showed with your calculation, the total resistance is not 0.66 ohms anymore. It's up to almost 1.1 ohms.
Okay, gotcha.
Because we took 2 of those 2 ohm resistors away and replaced them with resistors that had higher resistance. In one case, we took a 2 away and put a 4 there. And then in the third case, we took a 2 away and put a 6 there. And so since we were adding resistance to the system, that's why the total resistance had gone up from 0.66 to 1.09. But the current won't be 4.5 amps anymore because the total resistance changed. Even though the voltage is still the same on the battery, the current depends, yes, on voltage, but also on how much resistance the circuit is providing to the flow of electricity.
You got 2.73.
Yes, so, all right, I'll try now. So now we got a 3-volt battery in the numerator because current is voltage divided by resistance divided by 1.09. What did you get?
2.73.
Yep. So I maybe just did a little bit of rounding that's a little different than yours. I got 2.75 amps. Remember before it was 4.5 amps that was coming out of the battery, right?
Mm-hmm.
Now it dropped. Why did it drop a little bit? Now it dropped from 4.5 amps coming out of the battery down to 2.75 amps coming out of the battery. Why did that happen? Before we had all 2 ohms, right? So what do we do to cause that?
I thought it would actually be more since there is more resistance on the last 2 ohms.
Well, did we change the number of paths? Or was it always 3 paths?
There's always 3 paths.
Yeah.
But like, the resistors of those paths were all.
Before it was 2 ohms, 2 ohms, and 2 ohms. But now it's 2 ohms, 4 ohms, and 6 ohms. And so the path number is still 3 in both cases, but we have more resistance in this circuit, 1.09 ohms total, versus before it was 0.66 ohms. So the reason we have less current, 2.75 amps, is because the resistance went up or down?
Oh.
Yeah, the resistance went up
Inversely proportional.
because they're inversely proportional. Very good, yeah. So now we know there's 2.75 amps, I'll write it in, coming out of our battery. What will the voltage be on this first resistor? Remember that rule. It's on the top left of the screen still. So is the branch right here that the all the way on the left, not path 1, let's call it path 0, all the way on the left, where the battery is that branch in parallel with path 1?
Yes.
Yes, and so based on the rule, in parallel circuits, all branches get equal voltage.
Yes.
That's not supposed to say current there, so let me erase that to avoid confusion. So in all parallel circuits, all branches get the same voltage. So is path 0 and path 1 in parallel? Yes. What is the voltage on path 0?
The voltage on path 0 would be 3 volts.
3 volts, yep. So what must the voltage be on path 1 then?
3 volts.
3 volts. Is path 1 in parallel with path 2?
Yes.
Yes. So therefore, what must the voltage be on path 2?
3 volts.
3 volts. And lastly, path 2 is in parallel with path 3, so how much voltage would be on path 3?
Yeah, 3 volts as well.
3 volts. So lastly, how would you find out how much current is flowing through each of those particular sections?
We would multiply the voltage by the resistance.
Remember, you'd be now solving for current. That'd be the last thing. How much current?
So yeah, you divide
Yep.
voltage by resistance.
Yep. Exactly. So let's just do it real quick. What would 3 volts divided by 2 ohms be? Because as you said, current is voltage divided by resistance.
1.5.
So we would get 1.5 amps taking path 1. How much current would take path 2? Voltage divided by resistance.
0.75.
0.75. Let's stop and notice. Path 1 was 2 ohms. Path 2 is 4 ohms. So path 2 is 2 times harder to get through. How much less current did it send through path 2? Notice that path 1 is 2 ohms, and path 2 is twice as much resistance, 4 ohms. Now let's compare the current that flowed through both path 1 and path 2. Do you see a pattern there?
Introducing by
Can you put your mouth a little closer, if you don't mind, to the phone?
I said, it looks like it's reducing by a factor.
Well, let's look at the current in path 1. By what factor is the current in path 1 more or greater than the current in path 2? 1.5. Yeah, 1.5 amps compared to 0.75 amps. So by what factor is 1.5 greater than 0.75?
1.75.
No, meaning how many times greater of a number is 1.5 than the number 0.75?
Would be 1 second. 2.
2, yep. So the current flowing in path 1 is twice as much.
Yeah.
But now let's look at the resistances. The resistance in path 1 is twice as much, or the resistance in path 1 is the same amount as path 2, or the resistance in path 1 is half as much as path 2.
It's twice as much.
The resistance is 2 ohms in path 1 and 4 ohms in path 2. So the resistance in path 1 is half as much. 2 ohms is half as much as 4, right?
Well, yeah. Right.
So in that path 1, when there's half as much resistance, it sends twice as much current down that path.
Okay.
But when you look at path 2, there was twice as much resistance in path 2, so it only sends half as much current down path 2.
Oh, yeah, I see.
See that?
I was just saying it backwards.
It's okay. And because it always sends more current through the path of least resistance, path 1 has less resistance than path 2, it'll send more down path 1, 1.5 amps, compared to the 0.75 amps on path 2. And then there's proportionalities that you can apply again. Like I said, if path 1 has half the resistance, it'll send twice as much current that way.
Got it.
And now if we do the very last one, what will be the current flowing through path 3?
0.5.
Yep, voltage divided by resistance would be 0.5. And so on the AP exam, they might ask you to rank, what they call ranking, saying, rank the amount of current flowing through each of the paths from greatest to least. What would that ranking be?
It would be 1, 2, 3.
Yep, 1, 2, 3. Yep. And what will all of those currents now add up to? 1.5 amps plus 0.75 plus another 0.5.
1.75.
Yep. Does that get us back to what we started with in the beginning?
Yep.
Yep. All right. Good job. One other quick comment, and I don't know. I'm just not feeling that well. I might be able to spend another 10 or 15 minutes with you. Is that although I don't see it mentioned on your homework problems, the AP exam would definitely talk about power. Did we get a chance to talk about power last time? Wattage?
I believe so. I'm not sure.
Okay, so power is measured in watts, which is how rapid energy is used. And so the technical unit is joules per second. So if you had a 5-watt resistor, then it's using 5 joules of energy per 1 second of running. If you had, let me erase a little of this to make a little more space. If you had a 10-watt resistor, that means it's using 10 joules of energy per 1 second of it being on. So high wattage devices use more energy per second. Low wattage devices like 5 watts or 1 watt use less energy per second. And you can calculate that wattage, again, that's called power, by multiplying voltage times current. So could we finish this whole problem off, which I know it's not done on your homework problems, but on the AP exam they would bring this in to the question. And they'd say, what is the power or the wattage of resistor 1 on path 1 that we did? What is the power on resistor 2? What is the power on resistor 3? Remembering that it's just always the voltage. Yep, voltage times current. So in the first path, 3 times what?
3 times 2.75.
So actually the current, 2.75 is the current coming out of the battery.
Yeah.
So, okay, that's doing that sounds fine. You're doing the wattage of the battery. So 3 times 2.75 comes out as what?
8.25.
So this would be an 8.25 watt battery, which means every second it's losing 8.25 joules of energy for every second that it's on until all the energy is gone, and it's a dead battery. How would we find the power of resistance 1, which is in the first path?
3 times 1.5.
Yep, which comes out as 3 times 1.5 would be...
That's 4.5 watts.
Yep, 4.5 watts on this path. What would the wattage on the second path be?
Just writing it down.
It's okay, yeah.
So then it's
3 times 0.75, yeah, because it's voltage times
You get
current.
2.25.
2.25 watts, and then the last one.
And the last one is 3 times 0.5.
Yep, 3 times 0.5, which is
1.5.
1.5 watts. And this is a law of conservation of energy now, which is that if you add up the wattage on all 3 of them, what would we get? And compare it back to the wattage of the battery. Well, if we added 4.5 watts, which is on, and then added to that 2.25 watts, which is the wattage on path 2, and then lastly you told me 1.5 watts on path 3, and added those together, what will we get? 8.25 watts. Compare that back to your original wattage calculation for the battery, which is right here. See how you get the same value, 8.25?
Yeah.
So if these were bulbs, that's what the AP exam would do. These would all be bulbs, and they would tell you the resistances of each of the bulbs. Guess which one of these bulbs would be the brightest?
The first one.
Exactly. The first one would be a 4.5 watt bulb. The second one would be a 2.25 watt bulb. And the third one would be a 1.5 watt bulb. And brightness and wattage are related to each other. So whenever there's higher wattage on a bulb, then the brightness of that bulb will always be higher, more luminosity in that bulb.
Got it.
All right?
Yeah.
I'm going to just make one comment on, because I probably can maybe spend about 10 more minutes. I think you have the ability to, well, put this together. So let's try this. So I'm going to look at number 16 on your homework.
Okay.
Now you got a 990 ohm resistor, a 680 ohm resistor, and a 750 ohm resistor. So it might look at first glance like that's another just parallel circuit, but that's actually a complex circuit. Because electricity will flow out of here. This is the positive side of the symbol. This is the positive side, and this is the negative side right here. And so the electricity actually flows out of the positive side. So when the electricity flows out of this spot right here, what will that electricity, the current, what will it do when it reaches this junction right here? If we label this point A, what will the current do when it reaches point A?
They'll split.
They'll split. Some will go up, some will stay straight. The bit that stays straight will be forced through this path. And then what will this bit do? They'll combine right here, right?
Yep.
And then after they've combined, they're now all going to be forced, all the current will be forced through this one. So this section right here is parallel. And that parallel section is in parallel with, that parallel section is in series with this one. After all of that electricity recombines right here, then it would be equivalent of having it look like this. So you could pretty much take this parallel path right here, this is parallel, and find the equivalent resistance, which is like the total resistance just of that path, by doing 1 over 750 plus 1 over 680. I don't know what that all comes out as. Let's just say it came out as 2 ohms, just to illustrate this idea, okay? Let's say we did it all out, we flipped it, and we got that the equivalent resistance of just this parallel section is 2 ohms. That means you can take that parallel section out, and in its place, put this one here that has a resistance of the same equivalent resistance, 2 ohms. You see that?
Yep.
And then now the other one that's been sitting here all along, 990 ohms, these are now in series with each other. You see how we're back to our series picture?
Yeah.
And so what would the total resistance of this circuit be? In fact, it won't take me long. Let me actually just do it 1 over 750. I know that you could have done this too. Plus 1 over 680. And then flip it, 1 divided by that. I got 356.64. Sorry, 1 second. I'll write it down. So actually, when I did this out, it came out as 356.64 ohms as the answer to what the R equivalent actually is for that parallel branch. So what you do now is say, okay, well, that means we can take that parallel branch out that's circled on the left and just put one resistor right there that has the equivalent resistance of the parallel branch, which is 356.64 ohms. And now, how would we find the total resistance of this circuit? Because this is now where we've taken it and changed it into a series circuit. So what's the rule for finding total resistance for a series circuit?
Total resistance for a series circuit, you would add them all together.
Exactly. So it would be that amount plus 990, and we're getting the total amount for the series circuit that we've created right here is 1,346.64 ohms. How can we now figure out how much current must actually be coming out of the battery? They tell you in your homework problem that it was a 12-volt battery.
Yeah.
So how would you move on to find out how much current is coming out of the battery? How can we now find out how much current? Battery voltage is 12 volts, and the total resistance is 1,346 ohms. Could you use Ohm's law?
Yeah.
Yes, like we did before, and that would give you how much current is actually coming out of the battery, right?
Yes.
Which tells you when you go back to our picture, if I can erase some of this to make it a little cleaner. Okay, so now we would do current is voltage divided by resistance, right? To find the current coming out of the battery. So it would have been 12 volts for our battery divided by our total resistance of 1,346.64, right?
12 volts divided by, okay.
So I get 0.0089 amps, which would actually be, if you multiply by 1,000 to represent it in milliamps, that would be 8.9 milliamps. Or you could reference it in scientific notation, which would be 8.9 times 10 to the minus 3 amps, right? And so that's the amount of current coming out of your battery, 8.9 milliamps. That's not the number 8.9, it would be 8.9 times 10 to the minus 3, right? How could we find out now how much of that current... Oh, sorry, we have to go back. Can I backtrack just for a minute? I'm just going to backtrack for a minute. Go back to the picture on the right. all the way to the right, where we simplified our parallel circuit and turned it into a series circuit all the way on the right.
Yeah.
How can we find out how much voltage is on each of these resistors? How much voltage is on this one, and how much voltage is on this one? Well, we can use Ohm's law. The voltage should be however much current is flowing through our series circuit that we have here, multiplied by the resistance of each individual resistor, right?
Yes.
So the current flowing through it was 9, right?
Yeah.
So you'd have 0.0089 multiplied by the resistance that we had of 356 point. 64, right?
Yes.
So here we go, times 356.64. I get 3.17 volts, right?
Yes.
So I get 3.17 volts of the 12 volts is being used on that top resistor, the top part of the drawing. How would we find out how much voltage is being used to get through the 990 ohm? Do we know how much current is going through the 990 ohm resistor?
Yeah.
Yeah, it's the same amount as before, as the other one, right?
Yeah.
0.0089. So to find the voltage, what do we have to multiply together?
You have to multiply each system together.
Yep, current times resistance. So it'll be 0.0089 multiplied by 990 now, right? Because we're trying to find out how much voltage is used on this particular resistor on the right, 990. You with me?
Yeah. Yeah.
Okay, 990, enter. Oops, I made a mistake. I get 8.81.
Got it. Yeah.
What should those add up to if we've done all of our calculations correct?
8.81.
Plus 3.17.
It should add up to the current coming out of the battery.
Close. It should add up to the property of the battery.
The voltage.
The voltage. And when you add them, like I did, I got 11.98, which is pretty close to 12 volts. Not exactly because we did some rounding, right?
Yeah.
So now, what we're recognizing is this top resistor, the one that's up here, this one right here, and this is actually the number 990. And this one was 680. So the top resistor in our series drawing, remember it was the 356 ohms?
Yeah.
That was taking the place of the parallel of these two bits right here, right?
Yeah.
And did we figure out how much voltage was going to be dropped on that 356 ohms? We did. It was 3.17 volts, right?
Yeah.
That tells us that 3.17 volts will have to be on this side of our parallel branch. And how much voltage would be on this side of the other side of the parallel branch?
You would have to have.
Remember that rule for parallel branches.
You would also have to have 300
volts as well.
3.17 volts.
See that idea?
Yes, I do.
So before I kind of finish this problem out with you, this is a trick that what we're doing is, it's not my trick, it's a trick I was taught. All electrical engineers do this. When they start with complex circuits, they find certain sections like I had done, which has said, oh, this section of the circuit is parallel. We figure out what the equivalent resistance of that parallel section is. Then we imagine removing that parallel section from the circuit and placing one resistor in its place that has the same resistance as they did prior together. And then you work out the current like we had done. The current coming out of the battery, which we found out was 0.0089 amps, right?
Yeah.
Then we ended up using, Ohm's law again. We said, we stay in our little simplified drawing, which is now the series circuit on the right. We said, okay, if we know that the resistance was 356 and we know what the current was, we should be able to find the voltage on this equivalent resistor, the 356. We did. We worked it out to be 3.17. Then you re-expand your drawing back to what it really is, the parallel circuit, and apply that new law, that in a parallel circuit, the voltage has to be the same on both sides.
Yeah.
And so then you say, okay, if it was 3.17 volts on that 356 ohm, then back in the parallel circuit, it must be 3.17 on both sides. And then how much voltage will be on the guy that's 990? He's the series part of this circuit. He's not in parallel with anybody. The 990 on the right, he's just sitting there. All the current that comes out of the battery all has to go through him. Eventually, it all recombines, and all of it, all 8.9 milliamps, will go right through that 990 ohm resistor, which means he's in series, right? So we found out that the voltage on him was 8.81 volts, right?
Yeah.
So now we have all of the information we would need to calculate currents. Because now we know the voltage on this branch over here is 3.17. We know the voltage on the middle branch is 3.17. Did they give us the resistances of the left branch and the resistance of the right branch?
And then we can all get the Jewish system.
Yeah, exactly. They gave us those. Those are in the picture on your homework assignment. So we would just use Ohm's law now, right? I, again, is V over R. It's repetitive, you know. Some of these problems can be repetitive and a little bit tedious, but you kind of keep repeating the same exact ideas. So the amount of current flowing up through this left side of our drawing would be the voltage in that section, 3.17, divided by the resistance of that section, which was 750 ohms, right?
Yeah.
Would you repeat that same exact thing for the middle branch to get the current going through the middle branch? The answer is yes. In that case, to find the current going through the middle branch, it would be the voltage in the middle branch, which is still 3.17 volts, but now it would be divided by what resistance? Not 750 anymore. What is the resistance in the middle branch?
So
The resistance in the middle branch was 680, right?
yeah.
So when you do the voltage of 3.17 volts divided by his resistance of 680, that gives you the current flowing through the middle branch. That make sense?
Yeah.
And then the very last step would be, how can we find out how much current is going to be flowing through our last resistor over here on the edge, the 990 ohm? Well, it would be, as always, the current is voltage divided by resistance. His voltage would be 8.81 divided by 990. Guess how much we'll get from that one?
You'd get
Do you get 8.9 milliamps?
yes.
Yes, you do. Why does it have to be that way? Well, how much was coming out of the battery? 8.9 milliamps.
Yeah.
Does all of it have to finally be forced through that last resistor?
Yes, it does.
Yes, which is why when you do the 8.81 divided by 990, you get the exact same value, 8.9 milliamps. Does that help?
Yes, it does.
So I'm unfortunately going to have to go at this point because I'm kind of fading pretty quick right now. My stomach is really starting to hurt me. But I did hope that was helpful for you, Jeremiah.
You're welcome. Thank you so much.
All right, you're welcome, and have a good week. I'll see you next week.
You too. Get well soon.
What's that?
Get well soon.
Oh, thank you, Jeremiah. I appreciate that. Have a good weekend. Bye-bye.
You too. Bye-bye.
All right. That concludes lesson on series circuits, parallel circuits, complex circuits. Date was, or should I say date is, April 8th, Saturday, and time is 10:35 a.m. And that concludes. Signing off.